Hey guys, welcome back. SCHIZONE series episode 32. Long time no assembly. Topic today is going to be 3D scatter plots. Very simple, straightforward topic. Not too much theory to talk about. Just really the implementation and then obviously the examples. So we'll start with those. We have three examples today. The first one is just a random point cloud. So I can run this and you'll see, here's a random point cloud you can see. You can zoom in and out. Obviously we have the full cursor support. You can pan left, right, zoom in and out, rotate the model. So we have X, Y, and Z coordinates, obviously. We have tick marks. We have numbers on the axis as well. Axis labels, plot label. And of course you have those three-dimensional, the location, so X, Y, and Z. There's three variables there. You also have the marker color. That's a variable. You also have the marker size. See, there's some small circles, some big circles, etc. And then you have one discrete variable, which is like the marker type. We have all the PlayStation buttons here: triangle, square, circle, and X. We can add more if you want. Right now we only have 4. So yeah, this is the first example. Kind of cool. Everything is supported, rotationally speaking. Then we have example B. This is similar, much similar. But here you actually have two different data sets, and I'm plotting basically a sine of xy vertically shifted, and you kind of can see here how cool that looks. Kind of hard to tell what's going on, but yeah. So you can see we can plot multiple data sets on the same plot. That's what it's showing here. And then example C, this is subplots. If you're familiar with like MATLAB or others, this is a pretty common feature. Here I've got multiple different plots on the same rendering, basically, yellow, aqua, magenta, orange, and we can have these all located somewhere else in space. And all the coordinates are basically defined relative to the local origin, and we can move that origin around. That's the idea. So that's kind of the goal today. It took me the better part of a month to get this working, and there's not much to show for it outside of these examples, but this will help us down the road to visually express data in the future, hopefully. Let's get back to our slides. So yeah, scatter plots, not much to be said for this. You can plot data. Also, if you think about it, you can actually draw stuff to the screen. Any kind of geometry that you can represent by a point cloud, you can also show in this fashion. And then of course, whatever else you want to add, you can add. I don't think we have support for legends, for example, like a little plot legend, like a triangle is this, or this color is this. There's too much variation for that. So I was thinking if you wanted a legend, you could add it in yourself. You know how to put text on the screen, you know how to draw lines and stuff, so that shouldn't be too hard. And then here you can see this is actually like a 6-dimensional plot with those 5 continuous variables and then 1 discrete variable. So pretty powerful. And here is the implementation. So as usual, everything is defined with these data structures. And the idea is, let me just show you down here first. You basically call this function scatterplot3d, and that takes in that governing scatterplot defining structure, does a bunch of logic, and generates a series of, like a linked list of other structures that our rendering system knows how to render. So it will generate like a bunch of line segments for the axis, and if you want grid marks, it will make a bunch of line segments for the grid marks, all the right color. Then if you want to add tick labels, it will put text in all those locations. So you'll have like a text cloud basically as one of those structures in the linked list. Then you have something for the title and the axis labels, etc. And then of course you have the actual data in that linked list as well. So this function returns, basically it takes in this defining structure, we'll talk about that in a second, and it spits out like 6 or 7 smaller rendering structures which are fed by data in this input structure. And then what you do is you just basically pass that linked list into our rendering routines, and it renders as usual. So pretty simple implementation there. The key details are how do you define the structure, and here's just an example of how I did it. You could do it whatever way you wanted. So here's what I have. Here's that governing structure that you pass in to the scatterplot3d routine, and in this, just a bunch of pointers and a bunch of data. So first thing you pass in, or you put in the structure, is the title. So you have a pointer to this title. This is all null terminated strings, so this is the scatter plot title, random point cloud. Then you have titles for the axis, so X, Y, and Z. And of course, you could change this, and the text on the screen would change, right? That's the idea. It's a very general setup for this rendering system. So you pass in all those different pieces of text, then you pass in a linked list of all the data sets. Talk about that in a second, but that's where all the data comes in. The rest of the structure defines just the plot itself. So we have an origin translation. This is how you would define those subplots. You got to think, I want this plot to be at 0, 0, or should it be somewhere off to the side? Here's where you define that using floating point numbers. So if you want to put it at 7, 7, 7, you change these to 7, 7, 7, obviously. Then for the data, you can move the origin around. So this is for the actual data that you have to plot. Where should the origin be? Should it be at 0, 0, 0, or should it be at 10, 10, 10? Whatever you want your axis to cut through, basically. That's these three quad words here. And then you define for your axis the min and max. So in our case, we had negative 10 to 10, so I've defined that for X, for Y, and for Z, but you could change those as well. Then you can put the title wherever you want. And you could even use this to encode something about the legend as well. If you remember in our example B, I can even pull that up. I put, Z equals sine xy plus minus 5. So I didn't have to label the legends, with what's going on here. You can tell just from the title, hey, obviously the yellow is the plus 5 and the blue is the minus 5, right? That's the idea there. But yeah, either way, those three quad words describe where this text should be in space relative to the origin of the data. And so you got to think, if your data was, a lot larger than this, like it was millions, this location would be in the millions, right? If your plot wasn't from negative to 10, but from like negative 10 million to positive 10 million, this point would also be a very large point. Okay, going back, what's next? We then have the colors. So you see here, if you recall from before, we have these 4 bytes. The first byte is not really used, the high byte there, and then the rest is just RGB. And so you can see here, the x-axis is red, the y-axis is G or green, and the z-axis is blue. And then your font color here for the title, in this case, is white. RGB of maximum value is white. That's how that works. And then, of course, if you look at this example, the text and the tick labels assume the color of the axis. That's a pretty good assumption, I think. If you want to do something else, feel free to add more elements in that structure and handle them separately. Up to you. What else do we got? We have number of tick marks. These are major ticks and there's also minor ticks. And so you can see here, number of subdivisions per X, Y, and Z tick. This is how many times you want to divide between the ticks that you're actually labeling. So essentially, when I say 5 ticks, negative 10, negative 5, 0, 5, and 10, those are 5 major ticks. And then you can see here in between that, we have some minor ticks. So there's 2 subdivisions. That's what those bytes were defining. In fact, we could change that number. Maybe we will in a second, just to show you how this can be changed in real time. Or I should say at compile time. Or I guess at runtime. I don't know, depending. Then we have number of digits you want to display in the floating point numbers. You saw before, all those numbers had, I believe, 3 digits. I guess 10, we always, for the powers of 10, we always have 1 extra. That's just the way it works. But for everything else, you can see we have 3 sig figs, essentially. That's what this is defining here, these 3 bytes. And then we have the font size for the text rendering. This is actually font scaling. We have an 8-bit font, if you recall. So in this case, our title is 4 times 8 pixels, 32 pixels in, like, I think it's height, I guess. Or is it width? I don't remember. Maybe it's both. And then it's 3 times scaling, so 24 pixels for the axis labels, and then 2 times 8 or 16 for the tick labels. What else? Here comes something weird. If you think about it, how are you going to offset those tick labels and even the axis labels from the axis? So if you look here, like this 5 right here, it's not on the axis, it's off to the side, right? And this X is off to the other side. And then on the Y-axis, Y is up and down. Like why is the font, why is the text above the axis, and then Y below? Why isn't it co-located, right, etc. Look at the Z. The Z you have, hard to see, I guess, but you have like numbers on the side, etc. So that's all captured by, by this guy here, these offsets. So the X tick labels are offset in the Y direction, the Y tick labels are in the Z direction, and the Z ticks are in the X direction. So it's kind of like a triangle there of their offsets. And that looked pretty good. If you want to change that, go ahead and change it. It's not a huge thing to change. Just change the way these numbers are interpreted. Then we have a couple of other things. So this is weird. This is how thick the strokes should be. So if you see like the thickness of these, this is like a 2 pixel thickness essentially. The line is 2 pixels thick wherever you see it, I believe. That's what it's supposed to be, at least. And here you can change that number. And then you have a couple bytes here for how big each of those ticks should be as a fraction of 255, so the max value for a byte across the direction. So the idea is here, if you put 255, those ticks would extend the entire length. So here in this case, the X ticks are going in the Y direction, and they're going in the Y direction 5 out of 255. That's the fraction that this red is over this green. And if you make it 1, or make it 255, so the ratio is 1, this tick will be the entire length there of the, I guess, the Y direction, the Y-axis, the XY plane would be filled with these red streaks left to right. Maybe we'll try that out in a second. And then lastly, what do we have? We have some flags here. If you want to turn on the title, the X labels, the ticks, etc., you can set these flags here, these bits for this flag byte. I always like to have a flag byte. It's nice to have down the line to be able to turn things on and off just with bits here. In this case, everything is on. What's next? Now here comes the actual data sets. So if you recall our 30-second offset quad word here, this is the scatter data set structure. This is the linked list of actual data that you want to render to the screen. And this is what that points to here. And what are you passing in? Well, first, this is the linked list. So if you have multiple data sets, for example, in this example that I just showed you, there's 2 data sets that we're plotting, one yellow one and one cyan one or whatever. And so for this, we would have a non-zero number here. But if it's only one, you always have the linked list end with a null pointer in this slot. So that's the idea there. Then I have a slot here down the line. If you did want to have a legend and wanted to track the data set, like what their name is, this is like, this data has this name, etc. You can use this to identify where that is. Currently, I'm not using that quad word, but if you wanted to use it for whatever you want, it's there for you. And then here comes the data. So you can see I have a quad word for the X, Y, and Z. So basically, this points to a chunk of memory like this, in which you're storing all the X data points, Y points, and Z points. Then you also have arrays in memory. It's going to either be here in the binary or on the heap, up to you. Just for the sake of simplicity here, I put it here in memory so you can see. And then you have it for the marker colors. In this case, you passed in like things like this, 0xFF, FF, A5, 00. That would be orange, right? If you pass that in for one of these double words. And then marker sizes. This is a value just characterizing how big your data points should be. Like the characteristic size of a circle is the diameter, I think. And then for the triangle, it's like the side length, etc. And so you pass that in here. This is like pixels of characteristic size. And then marker type, we have 1 through 4. It looks like I didn't write down what they were, but one of them means circle, one of them means square, one means triangle, one means X. If you want to add a plus, you want to add a cross symbol, whatever, feel free to do that. No big deal. Okay, that's how that works. So basically you have quad words pointing to all those places in memory, either on the heap or whatever you have it, to describe all the data that you want to have plotted on the screen. Now, I also pass in this stride length. I always have this kind of thing in my data structures just because what if you, like this assumes that all of those quad words, so let's say your x coordinates were like 2, 3, 4, they're all adjacent in memory. But what if they're not? And why this matters is because what if you had like arrays of something else? Like what if this was like an array of things in your house, and it was like multiple things about that stuff. Like it had its location, obviously X, Y, and Z, but then also had, hey, this is the color of my chair. This is the floor of my house the chair is on. This is, you know, the material code. 5 means wood, 4 means plastic, etc. Right? So you had an array of just structures in general. Well, what you could do is for this stride length, you could pass in the size of each structure. You'd point to the first one, and then all of a sudden you could pull out of that array of structures all the x coordinates, all the y coordinates, all the z coordinates, all the material codes, all the colors, whatever else you want to pull out. You can pull that out even if the data is not adjacent in memory. That's kind of a nice feature to have. So I've wasted a couple of words of memory here to define those offsets. So this is a stride length of 0 because the data is touching. But if you had 100 bytes of garbage in between, you'd put 100 in this slot here. That's the idea. Okay, what next? That covers most of the structure here, all the way down to this. Then the number of elements, obviously we have 101 elements, so 101 here. Now here's the thing. So I assume for a data structure like this, for like scatter plot, you want to have X, Y, and Z coordinates. That's the whole idea of a 3D scatter plot. Now, if you don't want to make color a variable, for example, in this, color is not a variable necessarily, nor is the marker type, nor the marker size. They are constants. So I'm not going to waste memory describing, you know, 1,000 of the same color, 1,000 of the same marker type, 1,000 of the same marker size. I'm just going to, let me pull it up again, define a default value. That's the idea behind this. So here's the default color. Assuming you pass in 0 for this, this, or this, it automatically assumes these defaults. So here, I want everything to be red, basically. That's what this is saying. This is I want everything to be a, I don't know, whatever it would be. You know, a 5 pixel, whatever. And then here, this is the wrong value. Obviously, it has to be between 1 and 4. But let's say this meant X, right? Everything that would not be defined here is now defined by this overarching default value. So that's how that works. And then, of course, you have the things which you're pointing to in that structure. So these things are all pointing somewhere in memory, either on the heap or somewhere here. That's the idea. So it's pretty straightforward. I don't have any flags here. I pointed out here. You could down the line add a flag for, should this be in the legend? Should this be some kind of opacity thing? Turn it on and off. Like, you could add flags for all the data here if you'd like. Not currently implemented, but you could if you'd like. I always like to save a byte for this kind of stuff. It's very useful to have an easy on and off switch for certain features in your structure like that, in my experience. And then the usage. So I touched on this before, but just to go through it once again, this is the bulk of this entire example episode, this scatter plot 3D function. Again, it takes in basically a pointer to this structure here. So you define all this in memory, you pass in this address in RDI, you call this function, as you can see here. You need the heap for this, so I have to initialize that first. And then it will spit out in RAX a linked list of everything that's on the screen. So in this case, it will spit out a rendering structure for all the axes. So a red line from here to here, green line from here to here, blue line from here to here. So one structure for all that. Then that will point to the next structure. Let's say it's going to be all these tick marks. So you have a bunch of blue dashed lines there, red dashed lines there, green dashed lines there. So that's another rendering data structure that's being plotted to the screen. Then that points to, let's say, the title. The title is now a point on the screen. You pass that in. This carries the pointer to the text, the font size, etc. So there's one structure for that. Then that points to, let's say, the axis labels, so X, Y, and Z. Structure to characterize those. That points to a structure for all the tick marks. So -10 through 10, all the different axes, right? And then that points to a structure that characterizes this data set 1 up on top. So all these little yellow circles are rendered as one entity, one point cloud, and then you have this would be the last structure here, pointed to a point cloud for all those aqua colored X's. And then that linked list is returned out of this function. So how does that look? Basically, the very first element, that will probably be the axis line segments, gets dumped in RAX and returned to you. So basically here in RAX, you have the address of those, of the first of those, whatever, 5, 6, 7 rendered structure in memory. Then you have our usual rendering routine. Only difference here is that now you're passing in, you can see RAX is now passed into what I'm actually drawing. RSI is what we're actually drawing, and that's how that works. So yeah, that's pretty much it. I will now go through just the basics of the implementation really quickly here. Not too interesting. You can stop watching right now. So let's go to example A, just to see how this works. So in this case, we have a lot going on. So we have our frame buffer, that video memory we need to have in our heap. We also have a depth buffer. That's like 8 meg or something of space there as well. So you have to have quite a bit of heap, not only for the structures that we're talking about and the data that we're talking about, but you also have to have space for the video memory that we also use our own heap to do. So that has to be large enough to accommodate all your numbers. And then here are the includes. So those random point clouds, they actually are random point clouds. It's not real data, it's randomly created. So we have a couple of includes here for generating random float arrays, int arrays, and in this case, color arrays, or like the size of the markers, etc. So that's these 3 functions here. And then here's our scatterplot 3D function that does most of the heavy lifting in this episode. We have our usual cross cursor function here, nothing special about that. Now the first chunk of code here you see, this is actually generating those random arrays. So we randomly create between -10 and 10 a bunch of X chords, Y chords, and Z chords. Then we create a bunch of marker types between 1 and 4. And we create a bunch of marker sizes between 1 and 10. And we create a bunch of colors between 0 and white, or I guess between black and white. So yeah, that's how that works. And then we have defined in memory here a structure that I described before. So basically, we have our title, we have our axis labels, this structure here, the plot's at 0, 0, 0, the axis is -10 to 10, the colors are RGB. Let's change them. Let's make the x-axis, is this yellow? Let's make the font, or the title, let's make that orange, just to show you we can do this. Let's change the number of X ticks from 5 to 10, subdivisions from 2 to 3 in X direction. Let's make the Y ticks larger, how about much larger, and let's just run this. I don't know. Will this work? Hopefully not. Let's see. There you go. We've done something weird now. We have a bunch of weird yellow X numbers because we changed that from a nice number to a weird number. Our title is now orange. The Y markers are really ugly and tall. Yeah, kind of cringe there. But yeah, you can see how we can change everything about this plot whenever we want. So that's kind of cool. And actually, you could change this while it's running. As long as you recall that scatter plot thing, you could update this in real time. So yeah, that would be cool, kind of. How about example B? what's different about this one? So this one, if you recall, that was the sinusoidal wave thing, 2 different point sets. So this is just pretty much the same thing. Take a look at how that looks. So the only difference here is that we have to, in this case I'm using the heap for the data, so all the X chords are on the heap, same with Y and Z. The one interesting thing is those 2 point clouds share the same X and Y data. Like the same sets of X and Y points are valid for both of those sinusoids. Just the Z has to be different. So in this case, I have a common X coordinates array, Y coordinates array, and I have a different Z coordinates. So I have Z coords 1 and Z coords 2. And those get populated here by these loops. Basically just fills in, it basically computes sine of x, y plus or minus 5. That's how that works, and it renders to the screen. The difference here is that now you have 2 different data set structures. So for example, in the first example, remember this was the governing data structure. We had a pointer here for the scatter plot data. So you had 1 point cloud basically you wanted to draw on the screen. That worked. In this case, I want to have 2 different point clouds. So the first data set structure, the first point cloud, is a linked list that points to the second one. And the second one points to 0. That's how that works. So in that way, you basically have 2 different data sets on the same plot. And then you can see here all this N stuff. I've basically pulled out in a macro the number of discretization points in the X, Y, I guess X and Y directions, and we could change that. Right now it's 101. We can drop that down to, let's just say, 11. Run this again. You can see it will regenerate, hopefully. Now you can't really see the waves as much, but yeah, the whole plot still works. So cool stuff. You can now have multiple data sets on the same plot. Very cool. And then, of course, last example was 32C. I have to use sudo for this, in case you're wondering, because it uses the frame buffer device and a mouse device, so we have to have access to those things. Here was multiple different point clouds on each has its own axis system, basically. So yellow has its own, aqua, magenta, orange all have their own individual axis systems, and the data is located relative to its local origin. That's a cool thing there. So I could have data and I could put it on the corner of the screen always at this point in space. And so basically, this is literally just an object in space. Everything you see here is just an entity in space, a linked list of entities in space. And that's kind of cool, very useful actually, because now you can have a 3D model over here, you could have something else over here, you could have a scene over here. As long as it has its own position in space, you can put this plot anywhere you want in space. You can put this in your house, you know what I mean? If you had a house model, this could be on your table, etc. So it's kind of cool that you can do that in this setup. So how does this one work? Let's take a look. Much the same, of course. This one might have more things to render, obviously, because you have 4 different plots. And so in this case, we're actually cheating here. We use the same data for all of the different plots because you can't really tell because it's so small. But we copied the same data for each individual plot. And then you can see here, we call this scatter plot 3D function 4 times. So each call generates a linked list of oh, I spelled scatter plot wrong. Let's change that really quick. So basically, this first call defines everything about the top left axis system and point cloud. Second call, the top right. Third call, bottom left. Fourth call, bottom right. And then we just attach them all together. So we have the 7 whatever element linked list for the top left, and we just dump the top right one after it, or whatever. I don't know the order, I forgot the order, but you can see we just attached those linked lists together. We have a function here that does that, just here, found the end of the linked list, and then it just glues it to the end. That's how that works. And then we do define this in memory, so you can see the data set structure for the first plot, the second plot, the third plot, and the fourth plot. And each one has its own color. In this case, this is R and B. So this is the magenta one. This one is the orange one, looks like FFA5. And so, yeah, that's how that one works. So I'll run this again. All of those different plots are on the screen in different locations. Oh, and how did that work? Sorry, I forgot to mention the important thing on this one. You can see here for each plot, I actually filled out those 3 quad words here where it says plot origin x translation. This is, hey, where should the plot actually be in space? Should it be at 0, 0? No, in this case it should be at 0, -20, -20. So this plot is now shifted to the bottom, wherever that happens to be in space of the screen. I think bottom left. So that's how that works. And that's the gist of it. Now, I will go very quickly and very top level through the scatter plot function, so you can kind of get a feel of how much went into this particular episode. Lib.io, frame buffer, parallel, scatter plot 3D. And a lot of the includes I had to do. So a lot went on here. So the first thing that went on, the text rendering that we have, that was always left aligned, if you recall that. I added something that basically computes the length of a string, and you can center or right align or left align deliberately your text. So all the text is actually center aligned. That's the first thing I want to point out. Then, so much stuff. So we have to be able to print to memory. So we're able to print to the screen for how many months? Like a year over now, right? But to memory is important because all of those 10.0, 5.0 floats, they're in memory and they can change. I'm not typing that out beforehand and ending it with a 0 byte. That has to be made by the program. And so we have to be able to print floats or whatever to memory. And so this print buffer flush memory basically dumps the print buffer to a memory location, which seems very simple, and it is, but it's very important to this program's working. So that's that. And of course, this is all what's going on. So you can see how long this file is. This is, I guess, 1,000 lines of assembly code to handle all the different stuff that could happen just as far as parsing that input structure is concerned. There's more logic that has to go in for the actual point clouds and for the text rendering and for the line thickness and all that different stuff that was also done behind the scenes for this episode. I'm not going to talk about it too much. It's very simple in nature. But let's go through what's going on here. So first things first, I always put a sample of the structure. So if you ever want to write software with the SCHIZONE code base, you can just snag this structure and change the numbers. That's how that works. Copy and paste. The first thing it does is it checks for if you, well, first it flushes the print buffer, then it goes through, creates the axis structure, then I assume it creates the grid marks, the grid points, then it creates the actual text cloud for the grids. That's what it's doing there. Now it does the tick labels for the title, X, Y, and the Z direction. And then you can see here, the heap is used a lot for this. So a lot of these calls to heap alloc. And if it fails, if we're out of memory, every single time it just jumps to die, which is just some end, I guess that's down here somewhere probably. I probably should put like an error handling thing, but I hate that. So yeah, it just returns when it fails. It just returns out. But you could change it if you want down the line to process an error down here if you didn't have a space on your heap, etc. So yeah, then it does the title and the X, Y, and Z labels, and then lastly it does the actual scatter plot data, and it loops through potentially multiple data sets that you want to plot on the same plot. So there's a loop here that it goes through. So very simple. And then of course every single time it checks that flag byte to see, hey, did I actually even want to put Z text or not? If not, just skip. So there's the processing there to handle, hey, should this be active or should this be deactivated, etc. So that's that. I don't think I will say much more about this. I just want to say that this entire, well, this one's a bad example now because I changed the number. Let me quickly change that back. Let's go back to, what was it, 101? So this plotting system, this is just a single plot, right? We can do multiple of these. But I want to show you, like, how big do you think this is going to be in memory? Is it going to be a huge file? The binary for this? This binary is 29K, and a lot of that is just data structures that you don't even need to have defined in memory. You can define those programmatically if you'd like. But that's insanely small, is it not? 29 kilobytes for this entire 3D rendering like engine, basically, for a 1920 by 1080 screen to handle all the different types of scatterplot data, handle a cursor, handle mouse input, all that stuff. That's so much that goes on in 29K, and we could go way smaller. I didn't even try to code golf this. You can get way smaller than this if you really wanted to. I'm just showing that you don't need, and this is a static binary too. There's no other things being linked. And that's really why it's so small, is because only what's being used is being included here, nothing else. And it's not like aligned, there's no like special chunks here, alignment, whatever. It's very like bare bones. So I'm just saying you don't need a whole bunch of crap to do interesting things like this. Like this didn't require, 17, gigabytes of trash. This didn't require, 100 megabytes of trash. It didn't require even 1 megabyte. It's 29 kilobytes. So that's cool, in my opinion. So with that, I'll end the video. Thanks for watching. I hope you enjoyed. If not, I'll see you in the next one. See ya.